Welcome, ladies and gentlemen. The biological origins of our senses have a great influence on what we think about the things we sense. In our everyday lives, we usually compare the size of things to the things we sense, as one might expect. This human scale is what you might call the default setting in our human sensory system. The structure of this system is what predetermines the way we organize and make sense of what our senses are telling us. When we want to do this concerning planets and stars, we have to substitute ourselves for something much bigger. We still use comparisons, of course, but when sizes become too big to easily make sense of, we have to change scales. In the case of planets, for example, we use Earth as the standard unit of size. Then say things like, Mars is about half the size of Earth, Jupiter about 11 times, and the Sun is 110 times the size of Earth. When it comes to the size of orbits, we use the Earth's orbit. That is the average distance between the Earth and the Sun, or 1 astronomical unit, or AU for short. So for example, you could say Pluto's orbit has a radius of 39 AU. The planet scale and the orbit scale don't really get used together, so when we're looking at models like this orrery, or this illustration of the solar system, you're not seeing a realistic depiction, but instead something that might give one the impression that space is full of stuff. That would be quite the astronomical blunder, though. These days, we're sending spacecraft between planets, so having a more realistic understanding of the scale of space is helpful. One that puts into proper perspective just how little physical matter is out there. Don't worry, this is fun to do, and will probably blow your mind. Thanks to a spectacular coincidence, it turns out that if you adjust an AU down to a single inch, there are about the same number of them in a light year as there are inches in a mile. That means that if Earth is 1 inch from the Sun, then our nearest neighboring star is 4 miles away. At this scale, Pluto is about 3 feet away, and the entire solar system would fit nice and snug inside a person's outstretched arms. But wait, it gets crazier. At this scale, the Sun would be a dust mote less than 1/100th of an inch across, and the Earth would be microscopic at just 1/100th the size of the Sun, or about a 10,000th of an inch across, about the size of bacteria. I'm not sure where that puts us. I guess we're the bacteria who live on the bacteria. Now imagine floating in the darkness midway between the dust motes of the Sun and the nearest star. Now the dust motes are a couple miles away. If they weren't glowing with arc mode plasma, you wouldn't even see them. You'd probably think there was nothing out there but nothing, doing nothing. But that's only because way down here at the scale of the bacteria giving bigger bacteria a skin rash, we can't see much. We're like the Who's floating around on a snowflake. But what if our senses were adapted to the perception of Birkeland currents, whose width can be measured in astronomical units from down here? What if we could see the radiation they emit? What if we understood that they possess a power billions of times greater than the gravitational influence of these dust motes? The spacecraft that we're sending into space that requires us to develop a sense of the scale of space are fitted with technological sensors that can perceive these things. Of course, someone over at Big Space would have to actually use them to look, and if they did that, they'd be in danger of finding the only actual black hole that really exists. The one that's sucking every penny out of science funding and turning it into a crazy medieval superstition, equipped with its own version of spooky language that only the priesthood can speak, so they can act as the mediators between you and objective reality. Clearly, we need to update our view of space. But how? Our media is biased. No, not the mainstream media, who of course would never lie about anything, but rather the media of human sensation. Of all the things we might sense, we pick out only a few, and no wonder. Our senses were adapted to the exigencies of living on the surface of a stony planet filled with stuff that hurts if you run into it. As a result, we tend to classify solid stuff, things that are opaque, reflective, resistance to pressure, sharply bounded, as more real than other states of matter. Like the brick wall I smashed my head into earlier while trying to save my daughter's ice cream. That was very real. I could touch it. And I did. And it hurt. Strange as it may seem, it took people a long time to recognize the realness of things like air. You know, the transparent, indefinite boundaries, indistinct resistances. It took a lot of years of accumulating derivative effects before the gap was filled in our solid senses with the concept of gas. What's taken even longer is to fill that gap in around the concepts of electricity. The aurora, a glowing vacuum, may seem spooky and ethereal, but to create an aurora, electric currents have to flow in empty tubes that are several kilometers in diameter. The currents generate light, radio waves, and X-rays that consume more power than is produced by all our solid coal-burning, oil-fired, and water-driven generators. These currents are comprised of widely separated charged particles, at least compared to our usual experiences of density. Irving Langmuir called the medium that carried these currents plasma because of its lifeblood-like behavior, and the name stuck. But astrophysicists talk about it in euphemisms: solar wind, rains of electrons, impacts of ions, clouds of ionized gas, yada yada. Maybe they think those words sound more real than the thin ethereal plasma that it actually is. And 100 years ago, our vaunted experts could have been forgiven for these misleading descriptions. But it's time to get with the program, Gladys. Our perception isn't confined to the biomass we were born with on the surface of this rock. Now, most of what we see of the universe comes from the electronic sensors we put up there. Oftentimes, literally in the very plasma we should be analyzing. Ironically, these things are almost always using senses based entirely of electric and magnetic qualities. And for those of us that understand this, we look out on a reality that is made of plasma, where plasma is the primary substance. For us, the universe is composed of electric currents flowing in networks of circuits, coupled across scale differences from the galactic to the atomic. For us, the widely separated particles of stone and gas that we call planets and stars are barely noticeable dust motes. Ethereal specks caught in a web of circuitry. For us, plasma is very real, and all that stuff that leaves bumps and bruises follows it. Because of the fine-tuned instruments we build and the vast new perspectives they open for us, it's probably a good time to ask our physics departments to get with the times and stop wasting public money and human potential inventing things with math, and then pretending they're real. We are literally surrounded in the electric force, and it's amazing. It's as close to a magical force as we're ever going to see, and we know it's real, and can actually do experiments with it. Unlike the inane cadre of patches dreamed up to fix the non-predictive standard model. Still, the experts at Big Space think we should ignore it, and spend all our time, money, and bright minds on a theory where a magical explosion makes everything exist. Because math, I guess, can describe that happening, even if it has a harder time with the successful predictions. Well, maybe that's true, and the math all checks out on this Big Bang idea, but lest we forget, math can also describe the muscle density of Superman's Kung Fu grip. As we have about the same odds of experimenting with the Big Bang as we do with Superman, I'd say you need a similar bar of proof to confirm both. One that has not been met. Now that we can look out at the scale of plasma, it's obvious that the electric force is at work, shaping reality and doing things we can't even fathom. Just like how the microbes swimming around in our cells probably have no idea what they are a part of. We are likely just as clueless. As I wrap up, let me leave you with one more thought concerning scales. I think it's getting pretty obvious to most of us that things just keep getting bigger, or smaller, the further you look in either direction. And of all the forces we know of, only one scales infinitely in either direction. The electric force.